Hello and welcome. This is the Georgia Tech ECE 4580 Computer Vision Midpoint project for Team TurtleSeek. Let's get started. The idea of the project was to create a sort of room-roving robot where it would drive around the room, creating a map, putting obstacles on that map, and finding people, differentiating them from the obstacles, and then putting them as markers on the map, and then coming back to those people and doing a facial recognition algorithm and finding them from a database, or perhaps even adding new people into the database. But so far what we can have it do is the initial room scan to initialize the map, and this is what that looks like right here on the laptop sitting on top of the TurtleBot. We can define a search area, which I'll go into in the other slides. It'll scan that search area and save the human locations as markers, which it will return to and scan those faces. And if a match in the database occurs, it'll actually result in saying the person's name. We've actually implemented a lot of speech on the TurtleBot just to make sure we knew what kind of state it was in the process, so either if it was exploring or if it wanted somebody to come up and face it, it would actually just tell you. Applications of such would be if you could find children in a crowded area, and there's always the disaster situations for these sorts of robotics. Another one would be to register people in a waiting room, and you could free up staff by just allowing this TurtleBot to go up and ask people different questions and saving into the database itself. Now, how we approach this problem, it's this sort of solution flow that's actually cyclical, where first step being planning, where we'd all collaborate and talk about what needed to be done and how to do it and who should do it. And due to the nature of the problem, it mainly comprised 3 different fields, being the navigation and the spatial awareness of the TurtleBot and the search algorithms. This was pretty intensive. Then we had the facial recognition and database comparison, and then the body detection and actually placing it as a marker, and bringing this all together was actually really difficult, so that's why this implementation stage was so important. We had all these defined as different packages in ROS where they would communicate with each other, and also because of the nature of these different algorithms, by themselves they're, just to give an arbitrary number, by themselves they're, let's just say 90% successful, which really they are pretty successful, we can assume that. But once you put all these things together, that 90% success rate goes down into a pretty significant failure rate. So that's why this test stage was so important, just to make sure that everything was working and working together well. Afterward, we would increase robustness, get an idea of what to do to improve upon it, just to get it to be as more dynamic as possible, and then we'd repeat this process. First, being the navigation. Most of the labor done in this section was done by 2 ROS packages, being the navigation stack and the frontier exploration packages. We've thrown in some code ourselves, but really most of the labor is being pulled by these 2 guys right here. The navigation stack package is the one that brings in the map creation functionality, the orientation of the TurtleBot, and the odometry to actually keep track of where the TurtleBot is in space when it's moving. It also does the simultaneous location and mapping, where it would update the map if there was a new obstacle in place that was picked up by the Kinect. This is really good because you're never going to have a constantly stationary map in a real-world condition. The Frontier Exploration package allowed us to predefine this search square, which it would search for people inside of, and then allowed us to define these search destination points. Just to give you a general idea, this isn't exactly how we did it, but it's a very good representation. We've implemented the functionality into a finite state machine of 3 states, being the exploring and body tracking state, where it would drive around initially and look for people, placing them as markers like this, and then searching for them, as in coming back to these people, and for each person doing the facial recognition. Something we have to consider before we do the actual exploration, we have to make sure to save the map initially, and then orient it at the beginning, so drive it around a little bit so it gets an idea of the origin point, and then we can start navigating around the plotted area. Next we have body detection. This was actually interesting because instead of a conventional detection of the body itself, this was actually really helpful because of the view of the Kinect. We've implemented a sort of leg detection algorithm, and because of the leg detection, this was actually done by Washington University. It's all open source code, so it should be easy to implement yourselves. But this leg detection algorithm, what it does is essentially finds two similar cylindrical objects and identifies them to be legs, which it can assume to be attached to a person. And we use that to create a destination point marked as green right here in the map, which it would come back and search to. Something else that's actually really good about this is that it's unaffected by the upper body gestures. So if somebody was in a different position, here it wouldn't matter, because essentially as long as they're standing, or even if they're sitting, the position of their shins would still be the same, so it would pick up the person regardless. Next we have facial recognition. We've actually switched from the conventional OpenCV examples that utilize the Fisher faces and eigenfaces method, mainly because they weren't as reliable as we liked it to be. So we found this new method called sparse representation that is actually elaborated upon in this paper. A reason why we liked it so much was because it wasn't as susceptible to orientation, gestures, emotions, and especially lighting. All these non-ideal conditions are very important to consider, and this sparse representation method seemed to really find the person even with those non-ideal conditions. And that's why pretty much we went with it. Now how this works, or how we used it at least, is once the program would be ready to capture, what it would do would be to take 20 pictures very rapidly right after each other and saves them in this sort of format. It would align the face, and then it would crop it, and then it would normalize the lighting, and then do a fine transformation. So pretty much it scales, it changes and transforms all of these faces into these similar recognizable faces that we all put into the databases, and that's why we get our face archives. Just a quick understanding, these lines aren't actually for the code itself. It's actually for the user to understand what kind of state the program itself is in, being that this actually keeps track of the current face. If the code was off to a bad start, it could actually think that a face was somewhere else, think that an object that wasn't a face was a face. So really this lets you know that it's on track and it's about to take the right picture. And that's pretty much the system that we have right now and how it's all constructed. For the future plans, what we want is to ideally have it be able to scan the open world real time, so don't need to predefine a map, don't need to search for people and then come back to them when we're ready. Just do all of it real time, searching when we need them, saving people into the databases on the spot. Just because people can also move, so we just need to make sure to have things as quick and dynamic as possible. And some steps we should do in order to achieve that would be dynamic archive manipulation for real-time recognition. So we could be able to take people out and add people in when we needed to, especially be able to update people also if we needed to. Another one would be real-time map creation. So instead of initializing it before, like I said, make sure that everything is saved on the go, especially because we don't need to save an entire area. We could just save a section. Let's just say if we were doing a city block, we don't need to do the entire city block. We just need to do a section of it, like an intersection. We need to make sure that we're not rescanning people that we've already scanned. Next, we want to be able to differentiate between legs and similar shaped objects. There was actually quite the problem with the leg detection algorithm, because it would detect things that looked similar to legs, being table legs was our big problem, and then classifying them as humans. So we need to make sure that we can differentiate between stuff like that. Next would be to focus on key individuals. So next we want to be able to focus on key individuals. So instead of searching for everybody, we get a general idea of the person just by looking at their body and seeing that if it's possible to even be a match, and narrowing down from beforehand, just to save us time instead of scanning each person manually. Alright, that summarizes what we did and how we did it. These are actually two demos that we ran, being a perfect run, where it would find one person and recognize that one person, saying that person's name, and then a nearly perfect run with multiple people, where it detected 3 people when there were only 2. It goes back to that leg problem. It actually thought that a pair of table legs was a person. Also, it detected a person wrong, but after the second detection, it found that person to be correct. So there are still minor problems, but as a midpoint project, we definitely have strong fundamentals going on. So just follow this link and you'll get an understanding of what we have going on, and so far what we have put together. Thanks for watching. Hope you enjoyed it.
Goodbye. Yeah. Great. This one's not there. You can use it. It's gonna be. That's okay, it's definitely okay. Yeah, no problem. So we get 2 people. Oh, there you go.
I'm the new person, I'm minus 4.8, 3.9, probability 78%.
Yeah, look at me.
I'm the new person, I'm minus 6.0, 1.2, probability 81%.
1%. There you go. No problem. No problem.
Calling them into better night. Visit people under 0 at minus 3.6, 0.6.
That's me. Okay. Maybe I'll keep the video for you. You can give me. No, there's nothing for you. Will you be enough of the error?
Come to me, baby.
Yes.
You still have to have it night. 4, 3, 2, 1. Hello, you. Visit people at minus 4.8, minus 3.9.
Yeah, that's one. You're educating, so. I pay.
4, 3, 2, 1.
Hello, pay.
Hello, you. Visit people number 2 at minus 0.
I will go to there.
Minus 1.2.
I'm going to have to do that. Yes. Hello, okay. Yeah, great.